Starlink is one of those technologies that almost sounds fake the first time you hear about it. Internet from space. Not the cables buried under oceans, not from cell towers standing over cities, but from thousands of satellites moving overhead at incredible speed, forming a network above the entire planet. And yet, somehow it works. People in remote deserts use it. Villages with no fiber use it. Boats in the middle of the ocean use it. Emergency teams use it after disasters, and in some places, Starlink is now faster than the traditional internet options on the ground. But that raises a bigger question. How does this system actually work? Not the oversimplified version, the real version. Because the truth is, Starlink is not just Wi-Fi from space. It is a giant moving machine made of satellites, ground stations, antennas, lasers, software, and orbital geometry, all working together in real time. And in 2026, it is far more advanced than it was just a few years ago. In this video, we'll break down how Starlink actually works, from your dish on the ground to the satellites in orbit, and all the way across the global network above your head. At its core, Starlink is trying to solve a very old problem. How do you bring high-speed internet to places where traditional infrastructure is too slow, too expensive, or simply impossible to build? Fiber internet is excellent, but only where fiber exists. Cell towers work well, but only where towers can be built and maintained. In dense cities, that's easy. In mountains, deserts, forests, islands, polar regions, and war zones, it becomes much harder. That is where Starlink comes in. Instead of relying mainly on ground infrastructure, Starlink pushes a large part of the network into low Earth orbit. The idea is simple in theory. If a satellite is overhead, it can beam internet down to a user terminal on the ground. That terminal can then connect homes, businesses, vehicles, or entire local networks. But the important word here is low Earth orbit. Traditional satellite internet existed long before Starlink. The problem was that older systems usually depended on satellites parked much farther away, in geostationary orbit about 22,000 miles above Earth. That distance created a huge delay. Even if the connection worked, it often felt sluggish. You clicked something and the response came back too slowly. Video calls felt awkward. Gaming was terrible. Everything had a kind of built-in lag. Starlink changed that by placing satellites much closer to Earth, often only a few hundred miles up. That doesn't eliminate latency, but it cuts it dramatically. And that single decision changes everything. To understand Starlink, you first have to understand the difference between being high above Earth and being low above Earth. A geostationary satellite stays fixed over one point on the planet. That sounds useful, and in some ways it is, but it can only stay fixed because it is extremely far away. Starlink satellites do the opposite. They orbit much closer to Earth, which means they move fast across the sky. They're not hanging over one location, they are racing around the planet. That sounds like a disadvantage at first. If the satellites keep moving, how can your internet connection stay stable? The answer is that Starlink doesn't rely on one satellite, it relies on a constellation. Thousands of satellites orbit in coordinated patterns, so as one moves out of range, another moves into position. Your connection is constantly handed off from satellite to satellite, often without you noticing it. Think of it like a relay race in the sky. No single runner carries the baton the whole way. The baton keeps moving from one runner to the next. What matters is not one satellite, it is the continuity of the network. That is why Starlink needs so many satellites. One or two would be useless. Even a few dozen would leave huge gaps. But thousands create overlapping coverage, and overlapping coverage is what makes real surface possible. By 2026, that orbital web is far denser and more capable than it was in the early rollout years. And that density is one of the main reasons Starlink now works much better in more places. So what actually happens when a user turns on Starlink? The process starts with the user terminal, the dish. This is not just a passive antenna, it is a smart tracking system designed to connect to satellites moving rapidly overhead. Older satellite dishes often had to be aimed very carefully at a fixed point in the sky. Starlink works differently because the satellites are constantly changing position. The dish identifies available satellites, selects the best connection path, and communicates with the network in real time. This is where people often misunderstand the system. The dish does not just point at space and magically receive internet. It is a part of a live switching network. It has to constantly adapt to movement, signal conditions, satellite availability, and network load. In other words, the dish is not simply receiving internet. It is negotiating with a moving orbital system above it. That is the one reason setup matters. The dish needs a clear view of the sky. Trees, buildings, and obstructions can interrupt the line of sight. Because satellites are moving, even a partial obstruction can create repeated interruptions as different satellites pass behind it. That is why Starlink users are told to avoid blocked sky views as much as possible. It is not a suggestion, it is fundamental to how the system works. This is the part where Starlink becomes a real network rather than a neat space gimmick. When your dish sends and receives data from a satellite, that satellite still has to connect to the wider internet somehow. In the early versions of Starlink, that often meant sending the data back down to a ground station connected to fiber infrastructure. So the path looked something like this. Your device connects to your router connects to the Starlink dish. The dish talks to a satellite overhead. That satellite sends the data down to a ground station, and from there, the request enters the traditional internet backbone. Then the response comes all the way back the other way. That already works surprisingly well, but it had limits. If the nearest useful ground station was too far away, or if the coverage was thin in that region, performance could suffer. That is where the system became much more powerful. Modern Starlink satellites increasingly use inter-satellite laser links, essentially high-speed optical connections between satellites in space. Instead of sending every packet back down to the ground immediately, data can sometimes travel from one satellite to another before returning to Earth closer to its destination. That means the network is no longer just space to ground. It becomes space to ground. And that matters a lot. Because once satellites can pass data across orbit, the constellations start behaving less like isolated relay points and more like an actual orbital internet backbone. The biggest reason old satellite internet felt slow was not download speed, it was delay, latency. Even if a signal moves at the speed of light, distance still matters. A signal traveling to a satellite 22,000 miles away and back is covering an enormous path, and that delay adds up. Starlink cuts that distance massively by operating in low Earth orbit. The signal still has to travel, physics still applies, but the trip is much shorter. That is why Starlink can support things that older satellite internet struggled with: video calls, cloud apps, real-time browsing, and in many cases even online gaming. That does not mean Starlink latency is always perfect. Weather can interfere, congestion can interfere, terrain can interfere. The handoff process can interfere, and because the system is shared, performance can vary depending on how many people are using the network in a region at the same time. So Starlink is not magic. It is just much more modern network engineering than the satellite systems that came before it. And for many users, that difference feels huge. One reason Starlink became famous so quickly is that people could actually see it. Not the internet service itself, the satellites. After launches, groups of satellites sometimes appeared as bright moving chains across the sky, the so-called Starlink train. For many people, it looked futuristic. For astronomers, it was also a problem. Because a giant network in low Earth orbit does not just exist in technical diagrams, it exists in the real night sky. These satellites are visible because they reflect sunlight, especially when their orientation and altitude make that reflection easy to catch from the ground. Over time, SpaceX introduced changes to reduce brightness, including design modifications and operational adjustments. But visibility remains part of the story, and that visibility is actually a useful reminder of what Starlink really is. Not one satellite, not 10 satellites, but a huge moving population of machines circling the planet all the time. That scale is exactly what makes the network possible, and it is also what makes it controversial. This is the part that really matters if you are watching an older Starlink explainer and wondering what is different now. The answer is quite a lot. By 2026, Starlink is not just that satellite internet project from a few years ago. It is a much larger, denser, and more sophisticated network. There are more satellites. Coverage is broader. Laser links have made the orbital network stronger. Hardware has improved. Deployment has matured. And the system now supports more kinds of users. Not just fixed homes, but mobile users, maritime users, aviation use cases, emergency response, and other specialized applications. In other words, Starlink today is not just an experiment trying to prove that satellite internet can work. It is an expanding global service trying to prove that it can scale. That is a different challenge entirely. It is one thing to connect a few early adopters in remote areas. It is another thing to support millions of users across different geographies, climates, use cases, and traffic patterns. And that is why the 2026 version of Starlink is really a story about system maturity. The basic idea stayed the same, but the network around that idea became much more advanced. Starlink shines brightest in places where the alternatives are weak. A rural home far from cable infrastructure, a remote research site, a ship, a moving vehicle, a region affected by disaster where ground systems are damaged. Those are the environments where internet from orbit can be transformational. But that does not mean Starlink is always the best option everywhere. In dense urban areas with strong fiber access, traditional ground internet can still outperform it on consistency, price, and sometimes raw speed. In heavily congested Starlink cells, users may also see more variation depending on time of day and regional demand. And then there is weather. Rain, snow, and atmospheric conditions can affect performance. Usually not enough to make the system useless, but enough to matter. So the honest way to think about Starlink is this. It is not a universal replacement for all internet infrastructure. It is a powerful new layer added on top of the global communication system. And in some places, that layer is revolutionary. In others, it is simply another option. It is easy to think of Starlink as just another internet company, but it is bigger than that, because what Starlink is really building is not just a service. It is a new layer of infrastructure, one that moves around the planet instead of sitting still on it. That has huge implications for remote access, for disaster resilience, for military communications, for shipping, for aviation, for regions where laying physical cables is too slow, too expensive, or politically difficult. And it also changes the way we think about the internet itself. For decades, internet infrastructure was mostly terrestrial. Even when it crossed oceans, it still relied on physical cables. Starlink does not replace that world, but it adds a second architecture above it: orbital, mobile, flexible, and increasingly global. That is why so much attention is focused on this system. Not because the idea sounds futuristic, but because it is one of the clearest examples of orbital infrastructure becoming part of ordinary life. So after all of that complexity, here is the simplest, accurate way to think about Starlink. It is a moving internet network in low Earth orbit. Your dish connects upward. The satellites pass data across the sky. Ground stations and orbital links route that data into the wider internet. And software coordinates the whole system in real time as satellites race above the planet. That is why Starlink feels so different from older satellite systems. It is not just one satellite beaming service down from far away. It is a living constellation, dense, dynamic, and constantly switching. And by 2026, that constellation has become one of the most ambitious communication systems ever built. Which means the next time someone says, "Internet from space," the truth is a lot more impressive than the phrase itself. Because Starlink is not just sending internet from orbit, it is turning orbit into part of the internet.